When you look at these equations, okay, this is actually something you already knew. Just focus on this first equation here. If I say today you have HF solution with certain concentration of HF, can you calculate pH of this solution? Let's say you have 0.1 m HF solution. What is the pH of this solution? Can you do this? It's a weak acid solutions, right? That's the things we learned in chapter 12. So how do you know this? First thing is actually you see these equations, right? And I say you have HF solution. Then the concept you should have is actually weak acid solution. Photon concentration equals square root of Ka times your acid concentration. And you got your photon concentration. Take negative log of that, you got your pH. So that's the things you already know. Okay? Now the things we are going to learn is actually if today in this solution I add in a salt and I ask you, okay, can you actually recalculate pH of this solution? In this case, we say we throw in what? The sodium fluoride, right? So once your sodium fluoride dissociates, you form this sodium plus. Okay, we say if the ions belongs to your 1A or 2A group, they are neutral. Sodium is actually neutral, it's not going to affect your pH. F minus is a conjugate base of a weak acid, right? So this is a conjugate base of weak acid, HF. This guy will be basic. So when you store this salt into your solution, what you really do is actually storing a weak base into your solution. That means this one is going to consume your protons. So that direction goes to the left. So under this case, your proton concentration is going to decrease, okay? Very important concept that you need to know. So if your proton concentration is decreasing, what happens to your pH? Increase. Okay, so those are very important concepts. Okay, every time you see a reaction going to happen, okay, you want to think about, okay, am I going to actually increase or decrease my proton concentration and my pH values? And this is actually easier than you thought, right? Because you know what other thing you throw in. You know the effective one is actually this guy, right? F minus is actually the one you throw in. And you know your F minus is a base. Base actually consumes your protons. Therefore, the proton concentration is going to decrease. And therefore, the pH is going to increase. So this is another example. Today, you have amine solutions. You know the amine is going to interact with your water, produce your NH4 plus and OH minus, okay, with a Kb of certain values. So yes, this is actually a weak base. Then I throw in a salt. Okay, so this is a salt I throw in. Okay, so you know once it dissociate, you got these two species. So Cl minus is a conjugate base of HCl. And HCl is a strong acid, therefore its conjugate base is neutral. So you know this guy is not going to be the one that affects your pH. What is NH4 plus? NH4 plus is a conjugate acid of a weak base, NH3. So you know you're actually throwing in an acid, even though it's a salt, but you know it's actually an acid. You're throwing an acid into your solutions, right? So once you throw in the acid into your solution, what happened to your OH minus? Your OH minus will be consumed by the acid, right? Therefore, your OH minus concentration is going to decrease. Since you're actually throwing an acid into a solution, your pH is also going to decrease. The same concept, okay, but in the previous example, we're actually talking about acid. Now we're talking about base. But the idea is what? It's actually, okay, if you have a weak acid or weak base solutions, you're throwing something else, then you need to actually expect how your pH is going to change. Let's do some calculations, okay, based on the things we have learned. Calculate the pH and the percent dissociation of HF in solution containing 1.0 m HF with Ka of certain number and 1.0 NaF. Two things you want to calculate, right? One is pH, one is percent dissociation. Your HA concentration initially is equals to 1.0 m. And then you also have your sodium fluoride. Salt is 1.0 m. First, actually, you know you have a weak acid. And then you throw in a salt. NaF, you know it dissociates, become Na plus and the F minus, right? Na plus again is 1A group, so it will be neutral. You know this is actually a conjugate base of a weak acid HF. So you know it is actually a base. So basically what it says is actually you have a weak acid solution with certain concentration. I throw in a basic salt. Can you calculate the pH value? Can you just calculate the percent dissociation? So you have HF. It's going to interact with your water. They give you H3O plus F minus. Okay, with a Ka equals to 7.2 times 10 to the negative 4. Okay, then we write our ice table. From the question, we know the HF concentration is 1 m. H2O is just your liquid, right? So we don't care about that. H3O plus is actually something that we don't know. We want to solve this, right? It haven't actually dissociate. So we put 0 here. Now it's the key. You throw in the salt. So you know here you should put 1. So then we say some of the HF is going to dissociate, right? We put the minus X here. Concurrently, you should have a plus X for your proton and the F minus. Then you are going to reach equilibrium, which you add up the two. Then you have 1 minus X for your HF, X for your H3O plus, and the 1 plus X for your F minus. Then you use Ka to solve this, okay? So your Ka is going to be proton concentration times your F minus concentration divided by your HF concentration at equilibrium. So that will be X times 1 plus X divided by 1 minus X. So in this chapter, every time you see this weak acid or weak base, just do the small x approximation. So when you do the small x approximation, on the top become x times 1, bottom is also 1. And that's going to equals to, this is actually small x approximation, okay? Then it's going to equal to 7.2 times 10 to the negative 4. Where your x is actually equals to your proton concentration. It's going to equals to 7.2 times 10 to the negative 4. Once you have the proton concentration, then you know your pH is simply negative log of your proton concentration, which is equals to negative log 7.2 times 10 to the negative 4. And that should give you a pH value of 3.14. Once you got this, then you can calculate your percent dissociation. It's going to equals to your proton concentration over your original acid concentration times 100%. So that we have 7.2 times 10 to the negative 4. Original acid concentration is actually 1 times 100%. So you know the percent dissociation is 7.2 times 10 to the negative 2%. In our previous slide, we say sodium fluoride is actually a weak base, right? So when you add in these things to your original solution, the proton concentration should decrease, right? Your pH should increase. We want to confirm that, okay? So we want to calculate the pH, okay, without adding in your sodium fluoride. Okay, so basically it's just your HF solutions. So weak acid solution. Okay, then we know the proton concentration of your weak acid solution just can be calculated through the HF concentration times your Ka, right? Which is going to equals to 1 times 7.2 times 10 to the negative 4 will give you a number of 2.7 times 10 to the negative 2. Then we can calculate your pH equals to negative log of our proton concentration equals to negative log 2.7 times 10 to the negative 2. And that should give you a number of 1.57. If you did not add in the sodium fluoride, we know the proton concentration or the pH value of the solution is actually 1.57, right? Then you throw in a sodium fluoride salt, which we know is a weak base. Therefore, the pH goes from 1.57 to 3.14. So this is cool, okay, but how does this thing actually connected to the buffer solution? Okay, why these things actually become important? Okay, so we want to actually do a little bit analysis here. Okay, especially the first one. Okay, so let's focus on here. Okay, let me highlight the area I want you to focus. So at equilibrium inside your solution, what we are going to have is actually, we're going to have this, HF, right? We're going to have our protons. We're going to have our F minus. So the X we saw for these things at equilibrium after you throw in this sodium fluoride salt is what? The X is actually very small, right? 7.2 times 10 to the negative 4. What is the concentration of your HF? It's 1 minus less small number, right? So we know it's actually around 1m. X, that's the proton concentration, right? 7.2 times 10 to the negative 4. It's a very small number. How about your F minus? It's 1 plus 7.2 times 10 to the negative 4, right? So it's also around 1m, right? So what are the major species inside a solution? It's actually pretty much the same amount of HF and your F minus. If you have strong acid, strong base thrown into water, you produce H plus and OH minus. These two species will have no doubt to give you water. This is actually a strong base, strong acid. It's different from the weak acid and weak base. So if you have a weak acid, weak base, especially actually conjugated acid-base pairs, they can actually coexisting inside water in large amount. So that's the major differences between strong acid base versus weak acid base. When you have strong acid base, you don't have H plus, you don't have OH minus inside a solution. All you have is actually water. On the other hand, actually, if you have a weak acid base, they can actually stay as the acid or weak base form inside water with significant amount. And that actually make this type of solution very special. And the reason it is special is because if today I throw in a strong acid into this specific solution, that strong acid is going to interact with your F minus and then push the reaction to the left-hand side, okay, and produce its conjugated acid. But if today I throw in a strong base into my solution, that strong base is going to interact with my weak acid and move the reaction to the product side and form my conjugated base. So since right now inside your solution you have a large amount of weak acid and weak base, then when you throw in this strong acid, strong base, I have something to compensate those strong acid or strong base. Therefore, the effects of the strong acid, strong base to change the pH will be minimized. So therefore, that's why every time we throw in this strong acid, strong base into a buffer solution, the pH doesn't change much. It's simply because the major things or major feature of a buffer is that you need to have a large amount of conjugated acid base coexisting inside your solution.